Hello everyone, welcome to a new video by Pitch Lumen, where they are talking about the center of gravity well. I have watched this video previously, very briefly. I had a visit from a colleague a couple of days ago, and I told her about me doing YouTube videos, and I then went on to look on YouTube to show her, right, and the new Pitch Lumen video came out 17 minutes ago or something, so I looked at it, we looked at it, we had a good laugh, and then I tried to correct him in the comments, and now I will have a look at it on video and talk about it a bit.
Hello everybody, this is going to be a video kind of going over something that Space Audits is talking about, Alan and that channel and their talks. This is a little bit in line with, actually I've been having a comment with discussion with somebody as well, so this will hopefully...
This somebody could be me, possibly, I don't know, I hope it is.
I'm just curious about something for any globe advocates out there.
Hello, that would be me.
So this here is Newtonian outlook of the solar system, and you have like the center of mass. The main point here I'm trying to emphasize is this would be like the center of mass of the solar system, and it might be a little bit off center from the sun. I don't know if
that is correct. It actually is, because the second largest mass in the solar system is Jupiter, and so it's not exactly at the center of the sun. It is slightly outside of the center of the sun, but I believe, and I could be wrong, I didn't check it beforehand, but it's not that important really. It could be slightly outside of the sun, but I don't think it is. I think it's still inside the sun.
If it's still in the sun or not, but a little bit off center because you have the center.
Yes, it is a little bit off center. I completely agree.
Center of mass of not just the sun, but also all of the planets and the volume that they, or the width that they span. So the center of mass will be shifted a little bit. So this might actually be able to explain like eclipses and elliptical orbits and whatnot. However, this model of Newtonian cosmology has been dismissed.
And here I'd like to briefly add my 5 cents, right? Because it's a very, very common misconception amongst flat earthers that Newtonian physics was dismissed, because it just hasn't been dismissed. There was kind of a new and improved version of how to think about gravity, but that doesn't mean that the old version is now completely useless. I would see it more as you were digging some kind of hole in your garden, and now you bought or you borrowed an excavator, and previously you were working with a shovel. Does that mean that the shovel is completely useless? No, absolutely not. As a matter of fact, for almost all cases about Earth and about the close Earth orbit, the Newtonian calculations for gravity are absolutely sufficient. And I mean that the first time that you hear about something that is not Newtonian in the context of gravity when you study physics, as I am doing right now, I'm in my master's program in both astronomy and physics. The first time I heard about non-Newtonian gravity in my physics bachelor was like in the 5th term or something, and then we didn't even calculate with it. We just said that this is a thing that also exists, just as a mention. And in astronomy, I believe it was also like in the 5th or 6th semester, when we learned about the Friedmann equations that are somewhat relevant for cosmology, and they come from relativity, right? So even at a pretty high, I'd say, level, Newtonian, or let's say classical gravity, is still applied, and it's applied by engineers, it's applied by geophysicists, and pretty much everyone who doesn't directly bother themselves with either cosmology or gravitational physics or relativity itself. Everyone else uses Newtonian mechanics and Newtonian gravity. So if you say that it has been dismissed, this is very misleading, because it's just not been dismissed. It's just not the best understanding we have anymore. That doesn't mean that it's completely wrong. It's just not as accurate. And for simple cases, I have mentioned that in a previous video, for simple cases, under some conditions, relativity will give you back the same results that you would have gotten with classical gravity. Let's move on.
Because of relativity. Relativity took the place of this idea. So relativity claims that the Earth orbits around the Sun in linear constant due to space-time fabric being curved.
I mean, I have issues with
Around the
that.
Sun.
The sentence in blue, there's something off with it.
Idea. So relativity claims that the Earth orbits around the Sun in linear constant.
I don't know what you mean in linear constant. First of all, you're missing a noun there. In linear constant, what? Motion, velocity, cars? I don't know.
Due to space-time fabric being curved. So
But like in principle, that is the gist of general relativity. That the change in motion is not due to an inherent force, but is due to geometry, due to some underlying geometry of whatever the kind of fabric of reality is made out of, right? And we call that, that's very simplified now, but we call that space-time. It's 3 spatial dimensions, 1 time dimension. So we have 4 dimensions now, and they change in accordance to mass, for example, also with energy and things like that.
So this explains why the Earth is sitting, why the Earth still is valid.
Now that sentence, I'm very confused about. What do you mean the Earth is still valid? Is it invalid otherwise? What do you mean?
Linear constant is
Linear constant what? Motion, velocity, something?
indistinguishable from still.
Ah, you do mean motion. No, I'm sorry to be the one to have to break it to you. In both models, the Earth is slightly accelerated. That's because we are curving around something. So it's not linear constant motion. It's just that this acceleration is so little that you can't feel it as a human, and you have a really hard time detecting it, even with measurement devices. Although that is, as far as I know, possible with fancy interferometers and things like that.
Go Bible. So basically, you have the Earth is orbiting as the
Or gyroscopes, for example, can detect them somewhat reliably.
Sun carves out its little nook in the gravity well.
And that is the thing that I would like to talk about later, because that's not necessarily. I mean, I do understand where you get that from, because unfortunately this is shown a lot when talking about general relativity. But a similar picture can already be drawn in Newtonian gravity, and I would like to talk about that. I will talk about that in a bit.
And so this would be like the Sun's center of mass, and that's why I drew this down here. This line is to indicate that it's like in the center, and that these are equal. It's an equal parabola or whatever you want to call gravity well on all sides, and then you have the Earth orbiting in this here, orbiting around the Sun. Clearly, to us, it looks like a circle with angles, but relative Earth orbit path is claimed to be a straight line.
The relative Earth orbit path.
But relative Earth orbit path is
Never heard of that before, and I also don't think it is claimed to be straight, because Earth's orbit clearly isn't straight. It's a geodetic, as far as I'm aware, for the local space-time of the Sun, which means that it's the shortest path that it can go in that regard, while sticking to having a constant energy. That is the orbit. I'll talk later about orbits as well.
is claimed to be a straight line, and that is why when they talk about like a train moving or anything, like if you have something go by, constant and linear are the same as still from someone on and on.
I understand where the confusion arises. The issue is that Earth is not going linearly. Very important. But we're just so slowly going on an orbit that you can't really feel it. It's a very reasonable assumption for not particularly long time frames that we're going straight.
Object. But the thing is, actually, there's something that is different. Is that this would be like a knuckleball if the Earth was going through like this at a linear straight without rotation, but the Earth is spinning.
We are also rotating around our own axis. That is correct, yes.
So there is actually a spin along here. It's not just a knuckle. So this is actually, sure, linear constant is indistinguishable from still, but the Earth is not claimed to be a linear constant.
Correct.
So
Oh, so you mean that because we're turning around, we should feel that? Well, you can calculate the amount of force acted upon, for example, a human when they're standing on the equator, which is where this force would be highest, and you find out that it's like 0.5% or something of the gravitational acceleration, which is so tiny that we can't feel it, essentially. But you can measure it with a precision scale, for example, which in itself is a really nice globe proof, and I encourage you to look it up.
the conflict is if the sun is making a well that all planets follow, and the planets are making their own independent wells within, the sun will make an equidistant circular well, basically that thing.
But by circular you mean symmetrical. I assume.
Orbit around. And so, how does a circular equidistant dip in a fabric allow for the elliptical orbit?
I will gladly show you just in a bit.
So essentially,
but it's very possible.
What I would ask is, like, anytime we're gonna, because now, okay, so what I would ask for is a demonstration. So how do we demonstrate this? Well, if we take a ball and we put it in any fabric, it's going to equally pull.
That's a kind of bad. I mean, it's good in terms of visualization, but in terms of as an experiment, that's just bad, because a fabric just isn't the same as relativity will predict it. Because, guess it or not, or believe it or not, relativity is really fucking difficult. It's no wonder that it's usually not taught in bachelor's courses, and only started to, or only it's only being taught in master's courses usually, and sometimes only as an introductory case, like what I took last semester.
On all sides around that ball. So, or around whatever we put in that fabric, it'll cause a depression, but it'll be equal all the way around. And so, if you could show elliptical,
I can.
that would be one thing, because how do you get out of the center of mass being here? And yeah, that I'm curious about how the Earth can go, like, if this is a linear motion and the Earth is orbiting, there's a direction where we're going with the linear motion this way as we turn this way. Like, my thumb is going along the ball, but now on the other side, my middle finger here is turning against this.
That's
motion.
correct.
As my middle finger is going this way, my thumb is going this way. They're going, middle finger going this way, thumb.
You have successfully discovered the principle of tangential velocity. Congratulations. But yes, that is correct.
Thumb going this way. So these are two different motions, and they're not.
I mean, I guess you could say the velocity vectors point in two different directions. Yes.
Measured, but then also, if this is linear motion, does the linear edge speed velocity of the object become more of a factor? As these are linear motions going one way while the other on the other side, antipodal goes the other way. So yeah, just a question for anyone out there is, how do you get away from, because this I think could explain ellipses and epicenters being off of center of mass.
And as can this one. Please do keep in mind that relativity has been the accepted model for gravity for over 100 years now. Please, when you do these videos, I absolutely I'm happy that you're that curious about it, and I'm happy that you're actually making an effort on making, like, that you write it down on a whiteboard, and that you talk about it, and that you list your complaints, and I'm thankful for that. That is better than almost any other flat earther that I have encountered. But in all that, please don't forget that this has been the standard in science for over 100 years, general relativity, right? Don't you think we would have noticed that by now? If that has been an issue, I assure you it's not an issue, and I will gladly explain to you why. Because it's already it's very similar like that already in Newtonian mechanics, right? So yeah.
I'm just curious about this down here. Anyway, thank you all for the time, and I think I'm actually going to throw a few channels down there. I don't necessarily agree with everything from all of them, but I just want to throw a lot of channels out there to help kind of get around censorship and spread people that I watch or have seen or anything like that, just to help try to kind of get some of that out there for anybody. So yeah, I hope you all are doing well.
And from now on, it's just don't take this personally. From now on, it's just religious ramble that I would rather not engage in. There are a couple of channels down there. Most of them are very fun flat Earth channels that I personally. Let's not talk about it. So let's instead talk about the whole orbits and stuff, and a bit of a history of gravity, because actually in the comment section I would like to point that out further. I think that he's misunderstanding a couple of things, unfortunately. First of all, he says that because I've left a comment, so we can use Newtonian where Einstein cannot be used. That is absolutely incorrect. Light would have plus and minus directions. I genuinely don't know what you mean by that. Light is just light. It can have any direction. I don't know what you mean. Einstein says that the speed of light is constant. That is correct, but like, I don't think that Newton thought that much about the speed of light, because I think at that time it was still held to be infinite. Could be wrong on that. That is correct. A lot of the premises in relativity, but you're talking here about special relativity, not necessarily general relativity, are based on, for all basic purposes, the fact that light has a finite constant speed. Wells are also Newtonian physics. Yes, I will show you. And this sentence I find extremely interesting, and I think it shows a deep lack in understanding of classical mechanics, like even rather basic concepts, because Newton had gravity as a force and Einstein switched it as an acceleration, as I will show very briefly. In Newton's model, it can be either a force or an acceleration, which you can essentially choose depending on what you want to calculate, and gravity was first described as an acceleration by Galileo. We'll talk about that. And I will show all of that, and I will talk about it. Yeah. So here we are back at my trusty old OneNote notebook, and I do apologize already in advance, because I know that this might be a bit tedious. I hope it's not too tedious. First of all, gravity on orbits, Wells, and Newton versus Einstein. And I would like to give a bit of an historical idea of if it was an acceleration or a force. First of all, Galileo, sometimes in between that time when the bulk of his work on the subject of gravity came out, he did numerous experiments with constant downward acceleration. Note the word acceleration. He figured out that if you have the distance something travels, if you just let it fall down, is proportional to the time squared and some constant. I didn't write the constant down here. He figured that constant was had to be half of some kind of natural constant. This follows from analysis where you can get the idea that you integrate and then you get t squared halves and things like that. He also figured out that the acceleration was some constant he called g times the height divided by the length for an inclined plane, where essentially he let round things roll off of boards and tried to calculate the acceleration, the constant downward acceleration from there. And he combined these two ideas. And since all of the other ones were known, and with a water clock you can somewhat reliably calculate the t squared. From that he got g, and he published in 1638. That's almost 400 years ago. He published the value of g to be around 9.8 meters per second squared. Absolute work of genius. That idea is so beautiful that it is one of my most favorite experiments in physics of all time. And that was the first real mention of gravity as an acceleration, and I would like to mention that this was before Newton. Okay, so later, Newton, in these 3 years, published the bulk of things that he did on gravity, with a lot of help from Robert Hooke. He figured out that the force of gravity, now note that this here is a force, right? The force of gravity is this one, which is the constant big G, the product of two masses divided by their distance squared, if you want to be precise, the distance of their centers of mass squared. And he kind of gives the cause for that. That is mass attracting mass, but it can also be an acceleration, because the first Newton's first law tells us that, well, if force is mass times acceleration, well, then the acceleration must be the force divided by the mass. So it's just that. That's not like difficult. So under Newton, it can be both. It just depends on what you want to calculate for. Do you want to calculate the force between two objects, or do you want to calculate the acceleration on one object? What do you want to do, right? It can also be a potential. This is just mathematics. You have this basic force here, and from that you can go all kinds of places with it. For example, you can calculate the potential. Gravitational potential, sometimes expressed as Vg, is just G times m over r. And from that, this is a 1 over r term, you can draw these funny potential wells. And they look like that. And this is just within Newton. We are not using any relativity as of yet. So you can draw potential wells already within Newtonian gravity. And it's not even difficult. It's pretty easy, actually. We did that in high school. All right, Einstein, extremely simplified. The whole general relativity is so complicated. I could not do it any honors of trying to explain it right here. So try to be very simple. He published the bulk of his relativity, of the general relativity, between 1905 and 1955, where gravity is an inherent consequence of geometry. In the simplest case, the Schwarzschild metric, this is acceleration. Because in the Einsteinian picture, it's not a force in the Newtonian sense, but it manifests, it causes an acceleration. You could still calculate the force if you wanted. But within Einstein, it's not inherently a force. It just kind of turns out to be one, if you will. So yeah, that's you could yeah. Okay, now that we have gone that sorted out, right? So no, Einstein didn't think of it as an acceleration first. That the very basic idea from Galileo was already an acceleration. And now let's talk about orbits. So we're going back to Newton or Kepler and his friends, and I will show you how elliptical orbits are possible there. And just the very same principle just apply in general relativity. This is not an issue at all, because these potential wells are also symmetrical. So first of all, something that I would like to point out here is that orbits are so-called conical sections. You have a cone, like this one right here, and you cut it at some angle, and the leftover kind of trajectory, if you want, is the orbit. There are 4 basic cases. We have here the energy, and we have here the minimal potential. Now, please note that this is not the same potential as up here. I both called them V because physics is like that sometimes, where you give 2 different quantities the same letter. That might be annoying. But if the energy is equal to the minimal potential that is necessary to keep that orbit, you have a circle. The r has to be a constant because the 2 masses are not changing. This is sure as hell not changing. And so the r cannot change. It has to be a constant, and then it is a circle. The circle is the easiest conical section, where you cut it such that the leftover trajectory or the intersection of the cone and the cut are a circle. You have the second case where the minimum energy is smaller than E, but it's still smaller than 0. Please note that at 0, something would have enough energy to escape the whole system. In this case, the solar system, right? So this is a bound orbit. It has a closer position and it has a far away position. So it's an ellipse. It's a bit of a skewed cut here, and the resulting orbit looks like an ellipse. Aha, so there it is. And it's just the same thing within relativity, just with a lot more complicated equations on the left-hand side here. But for almost all planets within the solar system, apart from Mercury, they work flawlessly in Newtonian physics, but for Mercury, you need relativity to figure out the drift of the perihelion. So that was the first 2 cases. The third case and the fourth case at the same time. If now we have more energy than is required to leave the system, technically, or we have exactly the same amount of energy, which is not something that we observe in nature, but it's still worth pointing out. For this case, when the energy is exactly 0, we have a parabola. So it goes in, it comes back, but technically there's a point right here, back here, kind of, where it would exit the system, where it would kind of just like have enough energy to escape, but also not. So that this would be weird. It's never ever seen in nature because no body can have the exact same amount of energy necessary. And for this one we see a lot though, if the energy is higher than is needed to leave the system, we have an hyperbola. You have the sun right here and you have some object going really close by and then just flying away. Some comets do that and things like that. So the potential well can be circular, and all 3 or 4, I just wrote 3 here, types of trajectory are very, very much possible. This is not even something that should be new. Dear Pitch Lumen and any other flat earther that watches this, I do highly encourage you to have a look at that. This is nothing new. This is done. We did that in the 3rd semester of studying physics, and we did it in an unnecessarily complicated way because they wanted to be thorough with us. But you don't need to be that thorough. It is absolutely possible to, within 1 or 2 weeks, get a firm grasp on classical orbits that answer all of these questions and confusions that, and I'm sorry to say that you obviously have. Please read through them. I will leave a couple of useful resources in the description of this video. But with that, this is almost it. I have another thing to show you. And this is the other thing that I have to show you, is an actually useful depiction of what space-time bending would look like in general relativity, because you often see these kind of depictions, and I'm really not a big fan of them, because it looks like the whole solar system is within like a kind of fabric, which is not a good description. This fabric is two-dimensional. We don't want anything two-dimensional. Strictly, we want something four-dimensional, but that's impossible to depict. So we're going with something three-dimensional. This depiction is one of the best ones that I've found so far, where you can really see that if you get closer, straight lines aren't straight anymore. They are curved, but you still they are an inherent consequence of geometry. I'm not a gravity physicist, not at all, not even close, right? But this is still. I've done a couple of lectures about it, about relativity and about like these kind of things, right? And so I can tell you this is very, very good depiction. One of the better ones I've seen so far. The unfortunate truth is that this is not exactly popular, so you won't find that many nice depictions, although all of these kind of cube ones are really nice. And with that, if you enjoyed this video, I thank you so much for watching. If you enjoyed it, maybe can I suggest leaving a like, and if you enjoyed it a lot, maybe considering subscribing. Yeah, that was it from me. I hope you have a nice time, and we'll see you in the next video. Goodbye!